Hi, in this video I'm going to go through the week 2 poll for spring 2024 where it asks questions about coercion between data types, properties of data types, and it starts on the concepts of extraction and how we can use extraction tools to pull out sections of data from larger objects. So one thing that's going to keep coming up, and I've already restarted the video a couple of times, is this concept of type versus class. So type is how something is stored in memory, and it often is going to be one of two different things. It's going to be a vector atomic type, so like numeric, character, things like that, or it's going to be a list type, where you have essentially multiple containers, and inside of those containers, you can have different types of data. The reason why we bother mentioning this is because type is related to the concept of how it's stored in your memory. And something like numbers gets stored differently than something like characters. So for instance, in this current problem, the letter A can't be stored alongside 1, 2, and 3 if they stay as numbers. Since A is considered more complicated, A is going to force everything else to get coerced also into a character. So 1 becomes the numeral, big air quotes, around 1, 2 becomes the numeral 2, 3, and so on. In other words, after this combine forces these values together, that resulting object must be a character vector. So it's stored in memory as a character. It is one-dimensional. That's why it's a vector. And that's the answer. This next one is trying to get you to think through the kind of order of operations here. There's a lot going on this, so let me just start off with trying to answer this question. So I say for the lines 4 and 5 here, and I give you kind of examples of what it looks like below, what is the first function that must complete? So the first function that must, I should probably just make that singular. I think I've rewritten this question a couple of times. The first function that must complete is not this one. Even though it's on the left, this is actually, in fact, the last function that occurs in line 4, the assignment of values to this object 2. Well, you don't know what values to assign, so how could you complete it? So that's why it has to come last, is because it's the last possible thing to happen. As dot logical, this parentheses matches to this parentheses. So it's going to happen second, and that's because it can't do that until this C completes. Now, inside of this C, there's no other functions. This is just the numbers 0, 0.5, 1, 1.5, and A. C will do a bunch of things under the hood that you don't have to see, so it probably uses many functions to do this, but C is the only function you're currently calling in order to combine these values. So that is the answer. That's the first one that completes. As.logical is the second. This assignment is the third. This process repeats for the next section. So the very last thing to occur here is this last assignment function. Next, I point out that object 2 becomes all missing values, and then object 3 doesn't, even though they're very similar. Now, the key difference here, the reason why this one is different, is because of that inclusion of A. And this takes several kind of, if you'll pardon my word, logical leaps. So let me walk you through this process. If I break it down, starting with the first function, hence that last question, if I start it with the first function, this must complete first, forcing all of these to become characters. Contrast that to this one, where that process doesn't occur. They can remain as numbers. Well, it turns out if I convert 0 to a number, it's already a number. If I let it remain as a number, and then try to convert it to logical, it becomes the value false. If I convert 0.5 to a logical, it becomes true. In fact, any number that is not 0 ends up becoming true. In contrast, this does not remain numbers. These remain the character 0, the character 0, period 5, and so on. Because these don't remain numbers, we're starting to try and convert, when the as.logical occurs, we start to try and convert character 0 to a logical. And that's one step away too many, and it results in a missing value. So that's like the key thing. To answer these questions, it's this one, and this one. 0 can be coerced into a logical value. I did it right there. 1 can be coerced into a logical value. I did it right there. And yeah, the output of C function can occasionally be coerced into a logical value. Not always, but sometimes. So, true or false questions are always hit or miss. That's why this is not graded assignment, but it is important for you to be able to think through these processes because stuff like this happens all the time. I have a column of values, and maybe this is actually a legitimate process that I want to convert numbers to logical, but if you had accidentally included a letter anywhere inside that column, and sometimes even spaces can do this, it would trigger the entire column to be interpreted as a character, meaning your attempts to convert it to logical wouldn't work. And you would be like, why is everything missing? I can see the data right there. It's in the computer, but it doesn't work because you can't convert characters directly to logical. You'd have to do an intermediate step. You'd have to have a as.numeric in between this as.logical and the C. And if you did do that, then you would get false, true, 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 missing. If you had a as.numeric in between where my cursor is currently. Nifty, right? Done that plenty of times. Okay, so the next one, using the below object output in conjunction with the prior example, you should be able to determine what the values of obj4 will be. So that process that I just said is what's being applied here. The first part is just me demonstrating to you that I can convert character values that are describing a number to numeric successfully, but I do not succeed at coercing A into a value. What value would you put? It's like capital A, non-accented, that's like a very specific character. What value would you make it? So if I see that, I can see that it became 2, it became missing. That concludes my statement just now. So let's walk through here. I say, what is the value of object 4? I even gave you a little sneak peek that, yeah, some missing information will be coerced. So I gave you a bit of a hint. But as.numeric, we'll be able to coerce that into numeric. It's already numeric, no problem. Numeric, no problem. Numeric, new problem. Yeah. Character, problem, can't do this. So even though all of these became a character, as soon as this as.numeric goes off, that is actually when this becomes missing. That is the only missing introduced, because once the as.logical occurs, this becomes true. Nope, this becomes false, true, true, true. And then this one was already missing, so it remains missing. And so your answer is what? False, true, 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 missing. Really putting together those previous questions. Okay, so this next one, sometimes it's simple, sometimes it's not. The key thing is that it looks like a matrix or a data frame. You can already pretty much say it's probably a matrix or a data frame if you just know those are your 2D objects. We then go to the summary data. The summary data is showing the different types of data across the different columns. If you really were still not sure what you were looking at, you could then look at the structure. It's another handy little tool. I use structure much more than summary, although summary is great for other functions. Structure shows us that, yeah, that's a logical column. Here's the values, and it clearly logical values. Here's some integer values. Here's some numeric values. That all matches here. In the end, I think it's fairly clear that if you're aware that the difference between a matrix and a data frame is that a data frame can contain multiple types of classes, whereas a data frame has to be all the same class, then it's obvious. So this is much more of just have you memorized your different types of data. That's it. Not my favorite kind of question, but this is a very realistic process. This is the sort of thing that sometimes I don't know what I'm looking at. And so I call these summary values. I look at the data. I try to understand it, compare it to my known knowledge, and then I know how to move forward. I know how to handle that data from there on. So answer is data frame. Had you picked list, it's not a list class object. Oh, good, I did say class. So this was clearly a data frame class. It is, however, a list type, which is very confusing. But that's stored in memory as a list. So each of these is a container. It's a different section of the memory, but they're all organized together. You can kind of imagine them like containers in a chain of containers. So you start with this one, and then this one, and then this one, and so forth. Okay, so I don't think this one really works the way I intended. It's not my favorite question anymore. It's a very cool, I think, process. It shows you how you can do some kind of complex steps. But the main thing here is that I am using C to combine the output of two random generation functions. And if you weren't sure that's what these functions did, I included the help files. So runif, maybe, is random uniform. It provides values from a uniform distribution that goes from min to max. And you can actually see the output of this, kind of ignore this section because this is where it's overlapping with our norm. And then here's the rest. So if you're understanding this is just more me making sure that everyone's kind of waking up those neurons from statistics. This must be the random uniform. So here is from 0 to 100 is clearly what we've generated. So our min would be 0, our max would be 100. The R norm is going to be this bell curve that's kind of embedded within everything else. And that's one of the more interesting things about this is that we will often see trends within trends, right? Biology is a lot of things happening at once. And so you often get this kind of mixing of signals and it stops looking like your beautiful symmetrical continuous distributions that you're used to when looking at basic like introductory statistics. In real life, it's just messier. There's stuff like this. There's noise. And that's kind of actually, if I was trying to describe what I've generated a normal distribution that also has like just a baseline level of noise. Something that's just going to have to be parsed through. So maybe you'll have to set up a sensitivity level that if you're trying to find this peak, you probably should just ignore this because this is going to throw off all your standard deviation. However, if you cut off everything that had a frequency of 200 or less, you would completely remove everything else and you would find a beautiful mean right at that center of that distribution. That would actually work out quite well. So just kind of a fun idea here. Anyways, the mean of this normal distribution, again, if you weren't sure what those are, you just come down here, read through what these arguments mean. Mean has a default value of 0, but I've overwritten it because it's not centered around 0. The standard deviation is 1, and you may not know this, but this is definitely not a standard deviation of 1. This is a much larger standard deviation. It's 5, turns out. So the mean must be, just tracing it, I don't know, what, 30, 25? Probably 25. Sounds like a number I'd use. Finally, we have this histogram function, which is calling object 5 first. Okay, so that's the output of here. Well, object 5 must be going to this argument. If you don't understand that, it's because you're not quite parsing the rules of how data gets applied to arguments. Well, if I don't name them, it just gets applied in order. So this must be coming X. And then whatever I get put here, since it's not named, it must be going to breaks. Well, breaks can be lots of things. But if you started the homework for this week, one of those things is a vector giving the breakpoints between histogram cells. And that's exactly what's happening here is we have lots and tiny, tiny little bins. So that must be a very large number. So I only give you so many options. That number is certainly not 100. It is definitely 1,000. So we have 0, 100, 25, and 1,000 with 75 not being used. Cool. So the next one is just showing you an example of this tool right here. Ooh, didn't mean to do that. That's all right. It's showing this tool right here We generate the values 1 through 5. We then compare them to 3. And what's interesting is R does a process known as recycling. So even though this is much longer than the vector over here, it will repeat the shorter vector until they're the same length, if it can. Sometimes they're not multiples of each other, depending on how you structured it. So it becomes 1 compared to 3. Well, that is true. 2 compared to 3, that is true. 3 compared to 3, that is true because this is less than or equals to, and then 4 and 5 are both greater than 3, so it returns false. So there you are. This next one, we're going to produce 1 through 5 over here. That's in parentheses, it's going to happen. Then we're going to start trying to do an extraction, but we can't do that extraction from the data over here, and that's just, you have to know that adjacency is how square brackets work. That's weird. That's not a typical R like syntax, but that is how this R syntax works. So you will have to resolve this first. So this becomes 1 through 5 compared to 3. So like before, this 3 will recycle. So it'll be 1 compared to 3. That is true, less than 3. So check that box. Sorry, yeah, don't do that yet. I'll explain. It's going to happen, but I'll explain why. So 1 through 3, less than 3. 1 through 5, less than 3 will be true. True, false, false, false. So that's what's inside these square brackets. At this point, this has all been resolved with true, true. Let me hold up my fingers like this. True, true. Wait, yeah, true, true, false, false, false. So that's going to be extracted from 1 through 5. So that first value will be extracted. The second value will be extracted. The third value will not because it's false. The fourth value is false. The fifth value is false. So just 1 and 2. The next one, it starts off with the letters. Those are the letters of the alphabet. Let me make those capitals. So the letters object is just the capital letters. That's why I changed it to capital letters. There is a lowercase letters. That's the lowercase letters. But it's going to extract 5 through 1. So that's going to be E, D, C, B, A in that order. And then this can't, the square brackets can't extract from that until this C is resolved. So that's just going to create a numeric vector of 1 and 3. So that means we're going to extract E and C because these letters were reversed. So the first letter in this resulting data was E, then D, then C. So E and C. E and C. Cool. This last one is what values will the following return? This is just a simple logical vector that I am manually creating. I very rarely would want to do this. I'm almost always creating logical vectors from stuff like this, where I'm doing some sort of comparison, and there's a reason why I'm getting these logical vectors. But here I'm just demonstrating, technically you can just manually create it. It's just the reason it would be kind of shaky. But just as practice, that means it's going to not have to recycle this time. They're the same length. So this F will get applied to the first value after this parentheses resolves, so 1. So it's not going to extract 1. 2 is going to come from, be compared to this false, so it's not going to be extracted. 3 is going to get extracted because its corresponding logical is false as true. No 4, yes to 5. So the answer is 3 and 5. Okay. I hope that helped. We're just going to keep practicing this. We're going to start branching out into more two-dimensional extractions and go from there. So please reach out if you're having any questions.